Hi everyone, welcome back to Codviento. Today we are diving into binary search tree, one of the most fundamental and powerful data structures in computer science. We will learn how to insert, delete, and search elements efficiently in a binary search tree. In my short video, I explained 6 different tree types in data structures. A binary tree is a hierarchical data structure where each node has at most 2 children, a left child and a right child. Think of a family tree where each parent has at most 2 children. This is a binary tree. A binary search tree is a special type of a binary tree with specific ordering rules. The left subtree contains values smaller than the parent, and the right subtree contains value greater than the parent. Same value is not allowed. Efficient searching all again. Instead of searching every node, we divided the search space at each step. Imagine a phone book where names are stored alphabetically. Instead of scanning every name, you start at the middle and decide whether to go left or right, just like how binary search trees work. Used in real applications, search engine, databases, memory management, and auto-sorting systems rely on binary search tree logic. Let's dive into binary search tree, insert, search, and delete operations step by step. Okay, first let's define our node class. A binary search tree node has 3 things, a value, and left child and the right child. Let's create our constructor with integer value. Code is here, zoom in. Now let's define our binary search tree class and let's implement our operations. And everything will start with root node for binary search tree. Let's create our constructor without any parameter, and root will be null when we create a binary search tree. Let's implement insert methods, and it will be public and void and insert. It will get an integer value. We would like to insert it. So this dot root equal insert value. I will define a helper method here. I will explain it to you. Okay, let's implement our helper method. Insert value with integer value we would like to insert it. We have some condition here. If root equal null, it means our value will be our new node. Okay, so if value can be less than root value, so this means we need to traverse left side of the root dot left equal, and I would like to traverse left side of the root recursively, root dot left with value. So I will define here a node value also. Okay, perfect. And else if value can be greater than root value, so it means we need to traverse right side of the root dot right and with value. Perfect. And return root. And we implement our insert value here, root and value. Okay, perfect. If the root is null, we create a new node. Otherwise, we recursively traverse left or right based on the value. Okay, let's implement our search operation for binary search tree, public, and I will return a boolean if I find the value or not. So search integer value, we would like to check it. Do we have this value in our binary search tree? Return search value, root and value. I will implement another helper method here. Let's implement our helper method. It will return boolean again and search value with a node parameter and in integer. Let's implement our search operation, and we have if conditions here. If root equal null, it means we don't have any parameter to return, so return false. And if value equal root dot value, it means we found the value and we will return true. If value can be less than root value, we will traverse left side of the root and return search value root dot left with value. Otherwise, value can be greater than value, and it means we will return right side of the root dot right, because it can be equal, it can be less, or it can be greater than root dot value. We can simplify this part of the code like that. If value is less than the root value, and return traverse left side of the root, otherwise traverse right side of the root. This is our search implementation for binary search tree. So let's implement delete operation, and it will be no return method. Delete and integer value, we would like to delete it. this dot root equal, and it will be so similar with insert root view. Let's define our delete value helper method. It will return a node and delete value. So integer value, we would like to delete it. Deleting a node has three cases: leaf node, one child, or two children. For a leaf node, we just remove it. If the node has one child, we return that child. If the node has two children, we find the smallest value in the right subtree and replace it. Let's start our implementation of delete value. A root can be null, okay? If return is null, root is null, return null. So if value less than root value, it means we traverse left side of the root recursively and delete value. Else if value can be greater than root dot value, so it means we will traverse right side of the root recursively, and else it means we found the value, we will delete it. So we have three cases, case 1 and 2, 1 or no child. If root dot right equal null, it means the left of the root can be not null or null, we don't know. So for the both case, we return root dot left. If root dot left equal null, and it means we will return root dot right. What is our case 3? Can be have two children. We find the smallest value in the right subtree and replace it. So let's find the smallest value. Root dot value equal minimum value right side of the root. Then we will replace right side of the root with this minimum value. Then we will return root here, and let's define our minimum value parameter. So it will be private. It will return integer, and it will get just a not parameter integer minimum value equal root dot value return minimum value. So let's traverse left side of the root to find the minimum value, while root dot left not equal null, minimum value equal root dot left dot value, and root equal root dot left. Okay. We complete our delete operation also. What is our cases here? Firstly, if root is null, we will return null. Then we will traverse left side of the right side of the root to find our value. And here, it means we found our value to delete it. So for a leaf node, we just remove it. If the node has one child, we return that child. If the node has two children, we find the smallest value in the right subtree and replace it. Let's implement a main operation and check our implementations. So I will create a binary search tree and I will insert, let's start with 50 and implement other parameters also. Let's print line. If we have 50 in our tree, so tree search 50 for example, it will return true because we have this parameter. And tree.search, let's check, do we have hundreds? It will return false because we don't have 100 as a value in our binary search tree. So let's delete 50 and print line 50 search result again, and it will be false of course. Okay, let's run our main method and check the implementation together. Yes, and we have 50. We don't have 100 in our implementation. We don't insert it. So after we delete the 50, we got result false because we don't have 50 right now. So, okay friends, our implementation is completed. Okay friends, try to implement a data structure is very good way to deeply understand it. And for more coding videos, please like and don't forget to subscribe. Thank you for watching friends. See you in the next video.